When performing voltage drop calculations for landscape lighting fed from a three-phase feeder, where each light fixture operates at 277 volts single phase and is alternately circuited from the three phases, you should perform the voltage drop calculations on a phase-to-neutral basis for each of the phase legs. The reason for this is that each light fixture is connected to a single phase and the neutral conductor. The voltage drop calculation for each light fixture needs to consider the voltage drop between the specific phase and the neutral conductor supplying that fixture. If you were to treat the system as a three-phase system, it would not be accurate because the load which is the light fixtures are connected to single-phase power and are not evenly distributed across all three phases in a balanced manner. To correctly calculate the voltage drop, firstly determine the current drawn by each light fixture. You can calculate this by dividing the wattage of the light fixture by the voltage, which is 277 volts. For example, if a light fixture is rated at 100 watts, the current draw would be 100 watts divided by 277 volts, which equals approximately 0.36 amps. Secondly, determine the length of the wire from the power source to each light fixture. This is the one-way distance of the circuit. Thirdly, determine the wire size and material such as copper or aluminum used for the circuit. This information is needed to determine the resistance of the wire per unit length. Consult the National Electrical Code, or NEC, Table 8 for conductor properties. Fourthly, use the appropriate voltage drop formula for a single-phase circuit. The basic formula for voltage drop is voltage drop equals current times resistance. However, since you are dealing with a circuit that has a specific length of wire, you will need to use a more detailed formula. A common formula for single-phase voltage drop is voltage drop equals 2 times the current times the length of the circuit and feet times the resistance per foot of the wire. Divide the result by 1000 if the resistance is given per 1000 feet. Fifthly, calculate the voltage drop for each light fixture. Using the values you have gathered, plug them into the voltage drop formula to calculate the voltage drop for each individual light fixture. Sixthly, compare the calculated voltage drop to the allowable voltage drop. The NEC recommends that the voltage drop on a branch circuit should not exceed 3% and the voltage drop on a feeder should not exceed 5% for a total voltage drop of 5% to the furthest point of utilization. If the calculated voltage drop exceeds these limits, you will need to increase the wire size to reduce the resistance and bring the voltage drop within acceptable limits. Finally, repeat this process for each phase leg. Since the light fixtures are alternately circuited from the three phases, you will need to perform these calculations for each phase to ensure that the voltage drop is within acceptable limits for all the light fixtures. When performing voltage drop calculations, it is important to consider several factors to ensure accuracy and compliance with electrical codes. Firstly, conductor material. Copper and aluminum are the most common conductor materials, but they have different resistivities. Copper has a lower resistivity than aluminum, meaning it offers less resistance to the flow of electricity for a given size. This affects the voltage drop over a certain distance. Secondly, conductor size. The size of the conductor, typically measured in American wire gauge or AWG, directly impacts its resistance. Larger conductors have lower resistance. Selecting the appropriate conductor size is crucial to minimizing voltage drop. NEC Table 310.16 and similar tables provide ampacity ratings for different conductor sizes and insulation types, which are essential for safe and effective circuit design. Thirdly, circuit length. The length of the circuit is a critical factor in voltage drop calculations. The longer the circuit, the greater the voltage drop. Accurate measurement of the circuit length is therefore important. Fourthly, load current. The amount of current flowing through the circuit directly affects the voltage drop. Higher current results in greater voltage drop. Therefore, it is essential to accurately determine the load current of all devices connected to the circuit. Fifthly, power factor. Power factor is the ratio of real power or kilowatts to apparent power or kilovolt amps in an AC circuit. It represents how effectively electrical power is being used. A lower power factor means that more current is required to deliver the same amount of real power, which in turn increases voltage drop. If the load has a power factor significantly less than 1, it must be taken into account in the voltage drop calculations. For example, if the power factor is 0.8, the current used in the voltage drop calculation should be the actual current divided by 0.8. Sixthly, temperature. The resistance of a conductor increases with temperature. Therefore, it is important to consider the operating temperature of the conductor when performing voltage drop calculations, especially in high-temperature environments. The NEC provides correction factors for ampacity based on ambient temperature, which indirectly accounts for the change in resistance. Seventhly, single-phase versus three-phase. The voltage drop calculation differs for single-phase and three-phase circuits. In a single-phase circuit, the voltage drop is typically calculated using the formula voltage drop equals 2 times the current times the resistance. The factor of 2 accounts for the current traveling out and back on the circuit. In a three-phase circuit, the voltage drop calculation is more complex and depends on whether the load is balanced. For a balanced three-phase load, the voltage drop can be calculated using a different formula that takes into account the phase-to-phase voltage and the impedance of the conductors. Eighthly, allowable voltage drop. Electrical codes, such as the NEC, specify the maximum allowable voltage drop for branch circuits and feeders. For example, the NEC recommends that the voltage drop on a branch circuit should not exceed 3% and the total voltage drop on a feeder plus branch circuit should not exceed 5%. These limits are in place to ensure that equipment operates correctly and to prevent overheating of conductors. Ninthly, voltage drop formulas. There are several voltage drop formulas available depending on the type of circuit and the information available. The most basic formula is voltage drop equals current times resistance, but more complex formulas may be needed for longer circuits or circuits with nonlinear loads. It is important to choose the correct formula for the specific application. Tenthly, using software and calculators. There are many software programs and online calculators available that can simplify voltage drop calculations. These tools can automatically perform the calculations and can take into account various factors such as conductor material, size, and temperature. However, it is important to understand the underlying principles of voltage drop calculations in order to use these tools effectively and to verify the results. 11thly, unbalanced loads. In a three-phase system, if the loads are not evenly distributed across the phases, the system is considered imbalanced. Unbalanced loads can cause voltage imbalances and increased voltage drop on some phases. In these cases, it is necessary to perform more complex calculations to determine the voltage drop on each phase. 12thly, nonlinear loads. Nonlinear loads, such as electronic devices and LED lighting, can generate harmonics that can increase voltage drop and cause other problems in the electrical system. If nonlinear loads are present, it may be necessary to use special voltage drop calculation methods that take into account the effects of harmonics. 13thly, conduit fill. The number of conductors in a conduit affects the heat dissipation of the conductors. If the conduit is too full, the conductors may overheat, which can increase their resistance and voltage drop. The NEC specifies the maximum allowable conduit fill to prevent overheating. 14thly, voltage drop compensation. In some cases, it may be necessary to use voltage drop compensation techniques to maintain the voltage at the load within acceptable limits. This can be achieved by using larger conductors, increasing the supply voltage, or using voltage regulators. 15thly, documentation. It is important to document all voltage drop calculations to demonstrate compliance with electrical codes and to provide a record for future reference. The documentation should include all the assumptions made, the formulas used, and the results of the calculations. By carefully considering these factors, you can ensure that your voltage drop calculations are accurate and that your electrical system operates safely and effectively. Considering the specifics of a 277 volts landscape lighting system using a three-phase feeder, the calculation approach focuses on single-phase voltage drop because each light operates independently of one phase and neutral. The 277 volts configuration is derived from a three-phase system, typically a 480/277 volts Y system. In such a system, 480 volts is the voltage between any two phases and 277 volts is the voltage between any phase and the neutral. Given this setup, each light fixture is essentially a single-phase 277 volts load. Therefore, the voltage drop calculation must be performed on a phase-to-neutral basis for each phase leg. Here is how to approach this. Firstly, determine the current for each light fixture. Use the formula current equals power divided by voltage. If each light is, for example, 100 watts, the current would be 100 watts divided by 277 volts, which is approximately 0.36 amps. Secondly, measure the length of the wiring from the distribution point to each light fixture. This is critical because voltage drop is directly proportional to the length of the wire. Thirdly, select the appropriate wire size. The wire size should be adequate to carry the load current without overheating and to minimize voltage drop. Consult NEC Table 310.16 for ampacity ratings. For a small current like 0.36 amps, a 14 AWG or 12 AWG wire might be sufficient, but you need to consider the length of the run and the allowable voltage drop. Fourthly, calculate the voltage drop. Use the formula voltage drop equals 2 times the current times the length times the resistance per foot. The factor of 2 is because it's a single-phase circuit and the current travels both ways. The resistance per foot can be obtained from NEC Chapter 9 Table 8, which provides the resistance for different wire sizes and materials. For example, if you are using 12 AWG copper wire, the resistance is approximately 1.98 ohms per 1000 feet at 75 degrees Celsius. If the wire length is 100 feet, the resistance for that length would be 1.98 ohms per 1000 feet times 100 feet, which equals 0.198 ohms. So, the voltage drop would be 2 times 0.36 amps times 0.198 ohms, which is approximately 0.14 volts. Fifthly, check the allowable voltage drop. The NEC recommends that the voltage drop should not exceed 3% for branch circuits and 5% for feeders. For a 277 volt circuit, a 3% voltage drop would be 0.3 times 277 volts, which equals 8.31 volts. If the calculated voltage drop is less than 8.31 volts, the wire size is acceptable. If it is more, you need to increase the wire size. Sixthly, consider all phases. Since the lights are distributed across the 3 phases, perform this calculation for the lights on each phase to ensure that the voltage drop is within acceptable limits for all lights. This ensures balanced loading and prevents any one phase from experiencing excessive voltage drop. Seventhly, use appropriate safety factors. When selecting wire sizes, it is always a good practice to add a safety factor. This accounts for any future increase in load or any inaccuracies in the calculations. For example, you might choose a wire size that can handle slightly more current than what is currently required. Eighthly, document your calculations. Keep a record of all your calculations, including the wire sizes, lengths, current, and voltage drop. This will be helpful for future reference and for any inspections. Ninthly, consider using voltage drop calculators. There are many online voltage drop calculators that can simplify the calculation process. These calculators typically require you to input the voltage, current, wire size, and length, and they will automatically calculate the voltage drop. However, it is still important to understand the underlying principles of voltage drop calculation. Tenthly, use appropriate hardware. Ensure that all wiring and connections are done using appropriate hardware and techniques. This includes using properly sized connectors, terminating wires correctly, and ensuring that all connections are tight. Poor connections can increase resistance and voltage drop. By following these steps and considering all the relevant factors, you can accurately calculate the voltage drop in your 277 volts landscape lighting system and ensure that it operates safely and efficiently. Remember to always consult the latest edition of the NEC and any local codes for specific requirements. If the calculated voltage drop exceeds the allowable limits, you must take corrective actions such as increasing the wire size, shortening the circuit length, or reducing the load current. This will help ensure that the lights operate at their rated voltage and that the electrical system is safe and reliable. Performing voltage drop calculations on a phase-to-neutral basis ensures that each light fixture receives adequate voltage for optimal performance and longevity. This approach is consistent with the NEC guidelines and best practices for electrical system design.